All right, so we need a more general concept of projections. So a minute ago we did projecting onto a single vector, right? I'm more interested in being able to do higher dimensional projections because I'm going to be looking for the closest thing in this subspace to something else. You guys ever answer a math problem like, what's the closest thing to blah, blah, blah? Yeah? You guys ever do that in your life? Yeah. You do lots of like, what's the closest point, right? You like, okay, so I need to get to the pond, and for me the fastest way to get to the pond is going to be to walk on pavement until I'm on the closest point that's paved to the pond, and then I'll walk directly, right? Like you guys do that all the time. So that's kind of what we're after here, and this is going to give us a neat consequence. This is going to give us least squares projections. Sorry, least squares approximations. As it turns out, they may as well be called least squares projections. So, in order to do that, I'm going to supply myself with a couple of things. I'm going to supply myself with a little goal. So, my little goal here is going to be to project a vector B onto a vector space that's, or a vector subspace really, that's going to be the span of some vectors A, 1 through n. You guys with me on this? I am going to assume that all these things live in the same place, right? So this is going to be a vector in Rm. These are going to be a, well, this is going to be a subset of Rm. Right, so at least all the vectors live in the same place. You guys see why I would need that? Like it doesn't make very much sense to project a one-dimensional vector in two-dimensional space, or vice versa. Right. So what I'm doing is I'm going to need to assume they're all in the same space. I'm also going to assume that these guys, the A's, are linearly independent. If they're not linearly independent, just start pitching vectors until they are. Make sense? You guys see that when you're forming bases all the time, right? Okay. So, my goal is to this project, right? Project in this case means find B parallel. You guys with me on that? B parallel is going to be a vector that's in this subset, right? The span. It's okay, Rose. I know. It's disturbing to think about multidimensional projections. Cray bananas. Okay, you guys good with this? So I'm going to find B parallel that's going to be in the span. That means I can write B parallel out as what? If it's in the span, what can I say about it?
It's a linear combination?
Perfect. It's going to be a linear combination of, well, of the A's, right? So I'm going to be able to say, all right, so B parallel is like x1, a1 plus x2, a2, and so forth until we get to xn, an. You guys with me on that? Okay. Now, all y'all good enough at this to tell me what picture that is? Perfect. This is the column multiplication picture. Oops. Yeah, that's going to have to be something. I'm going to call this xhat. That's going to be the x vector that I'm after. Maybe if I was doing a really good job with notation, I'd be like x vector and then hat. That's just going to be my special vector x that I'm after. You'll notice that I'm not calling it x. The reason I'm not calling it x is I'm kind of thinking about the equation ax equals b here. And that x is not going to be this x. This is going to be like a special x that's like the closest you could get. You guys with me on that? Okay. So what are the what's the infill in that matrix?
A1 is a column, and then all the way to AN is a column.
Good. All the A's are columns in this matrix. You guys with me on that? Okay. So my first, step one is going to be I need to lay my hands on that xhat. That's going to be my goal. You guys with me? So, what do I know? Well, how did this go over there? I'm trying to present a little bit of proof strategy, right? I've got a kind of single dimensional concept, right? I'm trying to lift it. That can be a real tall order. So I've got my single dimensional concept just chilling over here, right? And I need to turn this thing into that. So what did I start with over here? Did I start with B parallel? No. Weirdly over here I started with B perpendicular.
Oh, yeah.
You guys see that? So I'm going to try to pantomime that same thing over here. You guys with me? I'm going to be like, alright, so what the hell's B perpendicular? Well, I know that if I take B and subtract A x hat, I'm calling this whole matrix here A. Right, so if I take B and subtract AX hat, what's that going to be?
Not parallel? Oh, wait.
Yeah, I took B, I subtracted B parallel, right? This should be B perpendicular, right? So what that means is that this guy is going to be perpendicular to all of the AIs. You guys with me on that? I1 through N, right? Why is that the case?
Because that's B parallel.
Yeah, so, intuitively, because you're taking B, you're subtracting B parallel, right? Alternatively, if you wanted to demonstrate that this has to be perpendicular, you can think about Lagrange multipliers from color theory. If they're not all perpendicular, you can go a little further, right? And get closer. You guys see that? The kind of picture that I'm using, right, in my head, is I've got my vector B sticking kind of out of the whiteboard, right? And I've got a couple vectors A in the whiteboard. So, here's a couple vectors A1 and A2. Those are in this plane here. So the plane of the whiteboard is the span of those two vectors, right? And now I've got a vector B that sticks out of this thing, right? So the projection is really what, who's really closest here? It's one of you two guys, right? Are sitting along the perpendicular line. And so what you're seeing is actually the projection. You guys see that? That's actually kind of how sight works, right? You're seeing light bouncing directly off of this board and passing next to the tip of the marker. You guys see that? The perpendicular line is actually light bouncing off the marker and then bouncing off the back, or off the whiteboard and then bouncing off the back of the marker. It's with me? So, my projection vector is kind of something like this, right?
Yeah.
Oh,
See that?
yeah.
Okay, so what I'm trying to say is that if we weren't perpendicular to the whiteboard, right, we could adjust to get closer. Once you're perpendicular, you can't adjust to get closer because the kind of distance here, right, are those circular shells. That's where Lagrange multipliers come in. The circle's going to be tangent to the whiteboard, so the radius is going to be perpendicular. Is that making sense? No? Perfect. Cool. take out 3 if it's not making sense. Intuitively, it's, dude, you took B, you subtracted B parallel. That's going to be B perpendicular, right? And it's perpendicular to all the AIs. You guys with me? Okay, so my next construction step is going to be to say, okay, well, if it's perpendicular, how do I phrase perpendicular? Yeah, the dot product is going to be 0. So I'm going to take this vector, I'm going to say, that means, right, this is the same thing as B minus A x hat, oops, B minus AX hat, dotted with AI is 0. You guys with me? So this is that same step right here. This is A dotted with B perpendicular is 0. Cool. I rewrote B perpendicular as it's B minus the projection. That's here. I rewrote B perpendicular as B minus the projection. If I was trying to pantomime this exactly, I would have been smart enough to write it on the other side, but you guys are smart enough to switch the order. Does the order matter in a dot product? No. Great. Cool. Alright, so I know that this is perpendicular, and what that means is that I could make a little matrix. So, against my better judgment, oh, I really should have. No, teaching strategy's gone. Okay, so I'm going to make my little matrix. And what I'm going to do is I'm going to try to write that entire statement down in one fell matrix multiplication step. Okay. I'm emphasizing by bracket that I'm thinking about that thing as a matrix. With me on that? We're going to need to figure out what size that thing is in a second. And then in here, I'm just going to write A1 transposes, A2 transpose, and AN transpose. Is with me? Okay, so what category of thing is B minus AX hat?
One row vector? Or no?
It's a vector for sure.
Yeah.
Right, because B is a vector, so in order for me to formulate this, both of these should be vectors, right?
Yes.
Yeah.
So this B minus AX hat is actually itself a vector. You guys with me? So if I had to write down a size, I would say that's a M by 1 matrix, right? Okay. How about these guys? Why did I twist them sideways?
Because then when you're taking the matrix multiplication, you'll be taking essentially a bunch of dot products with the A transposes.
Perfect. The A transpose is going to be me doing a dot product, right? So my whole matrix multiplication here, this thing is n rows, right? By, yeah, it's got to be by m. And that's why I transpose these vectors, right? So they're m long. You guys see that? I normally am not, like, normally I would just write the vector A1 in these kind of sideways arrows, right? To say that I've taken A1 and made it into a row vector. You guys see that? So I'm kind of mixing notation a little bit, but I really want to be clear that this multiplication, right, is just me doing matrix multiplication. You guys with me? So, Orion said, when you do all that matrix multiplication, what do you get?
0.
Yeah, you get the 0 vector, because it's perpendicular to all of the AIs, right? Okay, so I do all that multiplication, I get the 0 vector on this, right? Yeah. Yeah, so the dot products are each providing a scalar, right? But categorically, this thing is an n by 1 vector. You see that? Okay. So I've got this multiplication, right? I get the 0 vector out of it. Please just notice, what is this matrix right here?
A transposed.
Sick. That's just A transpose, right? I wrote it in a really screwy way to emphasize that I was doing dot products, but it's just the matrix A transpose. So if I had to rewrite this statement, I'm going to say that's A transpose multiplied by B minus A x hat. And this is going to give me the 0 vector. You guys good with this? This should feel pretty similar to this guy. I mean, really, it's kind of a rewrite of this guy, but I'm having to, like, sort out some multi-dimensional shit here, so you'll have to forgive me that I kind of have a line that I'm missing, right? So my next step is going to be to kind of distribute, right? And then I'm going to solve. You guys see that? So let's do that, distribute and solve. So I'm going to distribute. And this is where we have to be really careful because here order absolutely matters. Right? You can't just, oh, well, the dot product doesn't care which order you multiply in because here I'm not doing a dot product. Right? Gotta be careful. So I got A transpose times the vector B minus what?
A transpose A x.
A transpose A x hat is the 0 vector. Goes on board?
Yes.
Okay, now what?
You can move the A transposed A x hat to the right side.
Good. So remember, I'm searching for something unknown here, and the unknown I'm searching for is x hat. You guys see that? So I'm going to add that to the other side. So I'm going to get A transpose B is A transpose A x hat. Okay. I'm going to flip this back over again so we can look at the other side. So right now I'm kind of chilling right here-ish. Right, I've got my stuff kind of multiplied out. I've got the thing I'm looking for on the right-hand side. In this step, what did I do? To get from A dot B is A dot A P. I shit. You guys see that? I divided here, and you can't divide by that.
But what we can do is do inverses.
What we could do is inverses, so we need to know whether this matrix is invertible or not. And what do I know about that matrix A?
It's linearly independent.
Good, I know that it's made out of linearly independent columns. Okay, so if the matrix A were square, I would know that it's in... Fuck. Okay, so here's what I know. I know that the null space of the matrix A is the 0 vector. And this is where I needed you to recall something from one of the homework problems. Shit. So the thing I need you to recall, two things. A transpose A is something, and the null of A is something. Okay, so the two things I need you to recall. Can anybody tell me anything about the shape of A transpose A?
Isn't it square?
Perfect. That's the easy one. A transpose A is square. Sick. Okay, that might be helpful. Because if I knew that A was square, right, I would have known that A was invertible. Now I know that A transpose A is square. And what I need you to remember is that the null space of A I need you to know that the null space of A is the null space of A transpose A. You guys with me on that?
Oh. Yeah.
So because I know that the A's are linearly independent, the null space of A is the zero vector. Because I know that the null space of A and the null space of A transpose A are the same, I know that the null space of A transpose A is the zero vector, and I know it's square. So if it's got a null space that's just the zero vector and it's square,
You can invert it.
then it's invertible.
Okay.
You guys see that?
So because of all that, we know for a fact it's inverted.
Yeah, so I know that this matrix in particular is invertible, so long as I started with linear independence of my A's. So don't get attached to the idea that A transpose A is always invertible. It's not.
Only
If the columns are linearly independent, then it is. You can see that? Okay, so I need to get that thing to the other side. So, tell me about x hat.
X hat is A transpose A inverse A transpose B.
Okay, it's A transpose A inverse,
And also A transpose B.
yeah, done to A transpose B. You guys see that? And on this one, the order abso-freaking-lutely matters. Don't pretend it doesn't. You guys good with that? Okay, that's x hat. What was step 2? Okay, wait, hang on. Let's just check that against the other side, right? If I started with one vector, right? If my list of A's was one vector long, this should be the same thing I got on the other side for P, right? P was A transpose B divided by A transpose A.
Oh, and instead of division, we're doing inverse.
Isn't that fucking cool?
Oh, gee.
And it's funny because, like,
You guys with me?
yeah, it makes sense.
Okay, so why were we finding x hat?
Because that's the thing that makes it perpendicular. Right?
Good.
That guy, the belt product.
So what was I after initially? X hat first appeared right here, yeah. So x hat was A times x hat, which was me writing down a linear combination of the A's, which was me saying B parallel was in the span. You guys see that? So all told out of this, what I found out is I just found out a formula for B parallel, right? It's A times x hat. So B parallel is A times x hat, right? So A times x hat is A times that whole mess. So A times the quantity of A transpose A's inverse times A transpose times B. And now I know we've trained you all very, very well in algebra. And so I need to caution you because you have little muscle memory in your fingers for symbols. And the thing I'm concerned about is that you might like distribute this inverse onto these pieces.
It's the whole.
And the pieces are not themselves invertible. If you did that, right? If A and A transpose were invertible, you would switch the order, apply the inverses, everything would cancel, and you would get B parallel as B. You guys see that? The only time that happens is when the vectors A that you started with were a basis for the space that you were in. And then when you project something onto the space that it's in, you get it itself.
Yeah.
Right? That's not an interesting case, so suppress that shit. Right? I know it's hard to do because we did train you, like we spent years training you guys to simplify, and this thing doesn't simplify. Like this is what it is. You guys on board? Okay, where the heck am I going to get B perpendicular from?
B minus that mess.
Yeah.
Good. So, I'm going to get B perpendicular by taking B and subtracting all that jazz. Okay, and now here's the hardest part. You could put an identity matrix here and factor a B if you wanted to. I guess I may as well do that. Okay. Now, the other thing I found was xhat, right? So I'm just going to write that down so we have a little summary here. And then the hardest question that I can ask you today is, which one of these things is going to be important?
The one that finds B parallel.
Yeah, it seems like probably this one that finds B parallel is going to be the important one, right? And the answer, strangely enough, is actually xhat's going to be the one you're usually after.
Really?
Yeah. So the picture that's going on here, like the reason I'm doing this is I'm going to be trying to do least squares projection, right? And so the kind of setup that I'm going to use is that I'm going to kind of write down what it means to be on lines, right? So I'm going to have a matrix A that's going to have two linearly independent columns. They're going to be pretty boring. And then I'm going to multiply by coefficients for lines. And then on the other side, I'm going to have some like kind of data set sort of stuff that I'm trying to hit. And what's really weird about that is that like B is going to be like the data. I don't really care that much. B perpendicular is going to, B parallel is going to be like the data if you put it on the line. B perpendicular is going to be like your error. But xhat is going to be the coefficients for the line. It's going to be real weird. So put this formula in your head first, and then maybe just remember where the other two come from in terms of xhat. Is with me on that? Yes.
Why over there? Because A, it's not being done for A is doing for in that one here, isn't it?
Yeah.
Okay, that fucking
No, that's just me being idiotic.
okay.
Good point. Yeah, because there is a tendency to be like, oh, well, B parallel's the important one. And so very, very foolishly, I copied B parallel down, right? Because there is a tendency to think that B parallel is going to be the important thing. And it's actually going to be xhat. So without the A here, you're going to be looking for something in the domain of A. That's what's going to be the kind of important thing. You guys see that? Kind of all throughout this, right? I'm pantomiming the... I didn't even write it down anywhere. But I'm kind of pantomiming the equation AX equals B, right? That's why I started with a matrix A that's got columns, right? And I've got a matrix B. The columns, right? The B's are kind of in the range space. Is with me. Cool. All right. This guy. Don't do the distributive piece. It doesn't work. You guys want an example? Okay. Good.